Okay, merry morning. So I want to show you something here very quick. So let us go to the project file. This is the daytime control. So it will work for class A amplifier, motor controllers, switch mode power supply, SMPS, which is switch mode power supply unit. As I say, class C pulse width modulation. Anything that you have to use a pair MOSFET itself, you need daytime control. And daytime control is kind of important because let me see. Okay, I really had to put back a better thing to draw on the screen itself when I'm doing screenshot to draw. Anyway, so we have test bench. I create test bench. This is the actual code itself, right? I already run all the simulation. This is a cut time, right? And I use Verilog as the programming language. So this way you're watching over here now is a class A amplifier, SMPS, stuff like that, right? This is the design of it, right? So hardware description language. Now how does design? I all the ICs we have out there. If you have a SG 3525 pulse width modulation IC for power supply, I believe those have some daytime control. You could determine that with a resistor, right? Um, but it's not programmable. It's an analog because you're using like an error amplifier, and the inverted and the non-inverted they can use a triangle wave from the timing capacitor, and the resistor they can use that for current control to determine a voltage in the error amplifier. So let me just open some fact. So this is what it look like here. I'm trying to we have a pen in this thing, but brush this that. Let's use this, right? So this is a comparator here. We have non-inverted, we have inverted, we have this here. It's in, and this is it here. So what you do, you have your reference, which is right here. We have a reference, but we have a triangle wave going this side here, right? With the center here could be like 0, right? And not 0, but let's say this is this area here is let's say this area here and this area here, right? We consider here to be 1 volt and consider here to be 2 volt, right? And this area here now will be 1.5 volt. Cool. So 1.5 volts center between both of them, right? So this over here now, this triangle wave is when we have the IC itself here and we have the timing capacitor, right? The timing capacitor now is what we see in this here, right? This is the SG and the TL and whatever, right? So anyway, I'll move that out, right? So they also have a resistor they could set for daytime. Now for daytime control, that resistor we will have something like, we say this is the 5 volts reference. We put 5 volts here, and this resistor go in here now. Let us kind of like put this to ground, right? And let us run an next resistor here, and this resistor will be coming. Let's kind of train this over here, right? 3D ICs, right? So this resistor connect over here. If we have, let's say, a 100k, 100k ohm resistor, it will actually change the voltage. It pull along and it will pull this voltage down over here and this new thing here now, right? Pull it along a little bit. Now the pulse width will be like this, right? Right, and so I was trying to make this a little more better, but when you look at it, it will be like you see this is the new reference. We pull it down, right? So they say we pull it down with this resistor here now. The over here now the reference would be like this. So just kind of put it so. So from here to here we have a on time, and from here to here we have a off, and over here now we have this off time here, right? And we just come up with the off time here. Then we have this coming up to on time, which coming up to about here. And we come here and we do the same thing here. We have the off time, we have the on time, and we had that here, right? So what happened is that it changed the duty cycle, but when they actually do this, they will actually have the inversion of this, and next one like this will be negative, positive, and this will connect here, and this will connect here, and they will get the opposite of this. But what they're actually doing to as well, they will process this with the long logics itself to try to get the dead time to be like this, right? Like that, like that. Let me just get a PDF. Okay, so we look at the PDF. The SG32 something, right? I say it probably had dead time, but they have dead time on it, but it do have a dead time control. We have soft start. Soft start is basically a capacitor out here, and the voltage will take a while to come in here. They have a current, a constant current over here, which is 50 milliamps. So whatever capacitor you put here will take a while for this to be able to charge, and it'll be ramping up, and it'll be changing the PWM over here, right? So we had the error amp itself for current and voltage regulation, right? We have the capacitor with the triangle wave itself, which is timing capacitor here, and we have a resistor coming up here to go back here to be able to discharge the ground, right? So that way your ramp, because square wave coming here and causing it to discharge. If you want to have like lots of gates and you want to use the IC to drive more gates as possible, this wouldn't be able to do a bunch at the same time. What you could do, you could actually use sync. You connect this to the other IC and have one working, right, with the timing resistor and the timing capacitor, and the other IC itself, you don't put no timing resistor and capacitor and connect the pin tree, all pin tree together, but one have to be master, and you will be able to synchronize to have more gate drivers, right? So this do have no dead time control externally, right? You look at the TL here, that was the SG, right? They have the timing resistor and capacitor here, dead time control. So look, we have a dead time control at the TL, right? So the dead time control here now, where we had the dead time control, like the DT, right? DTC, dead time control. So they're showing you here, they're doing a ramp, and that basically like a soft start, right? So when you look at it here, watch here carefully, right? So the dead time control literally showing you that it have from this space here to this space, right? This region here, they have dead time control here. So the dead time control here, and it actually going up much more from here to here and here to here, right? More dead time control, right? And this is the voltage and the capacitor, timing capacitor, and you can notice more voltage, more dead time control, right? So have more dead time control, and when we remove the dead time control, we can see it pretty much there over here. So right, so this one fitting inside here good, right? So wait, now we have other controls here, right? So we have feedback. So this region over here, we have zero feedback, and we have that here. So this is where you're seeing perfect, but they have a little dead time over here that won't cause the MOSFET to blow out, right? You could barely see it, but it exists here that we can't zoom in much to see it, right? So in this region over here, we have no DTC and no feedback from the error amplifiers itself, right? So the error amplifier, we have no feedback coming to it. So we see the exact 180 degrees, no dead time control additional to it. But the minute we send feedback, we pull on the dead time control and we put feedback, we can see the feedback will control the dead time control again, the PWM, right? So that was how regulation is take place. So let me see this is it here, right? So we had the feedback here and data control here, they over here. So it actually go to the OR gate, right? And whatnot. Now this is what they're using. You can set a voltage here, right? To analogically have a daytime control, right? But you know that is analog, right? So it can have fluctuation variation when it come to the resistor tolerance that you're going to use, right? It will not be precise exactly because it's analog, right? Before I go to digital, right? The digital don't make the determination, the analog determination. So I knocked this out completely, and I literally going into right. So we'll get rid of this now because I don't explain that here. So what I did now, I have now let me go back into this. So I'll explain what I literally have here, right? Let me look at something a little more better. Right, so what I have over here now, let me look at the size, whatever. Right, so that's good. So let us say we have an IC here, right? I could create 1, 2, 3, 4, right? 2, 3, 4, and I have like pretty much, let me say we have a 5 volts itself, 5 volts. Oh boy, I kind of like zoom out, zoom back out, zoom in too heavy. Right, so let us go back here, right? So I can have like 1, 2, 3, 4, 1, 2, 3, 4, right? And let us say let's draw a resistor for one, but it goes for all, right? And we have a 5 volts, right? 5 volts. So we have 5 volts here. We have our pull-up resistor, wherever the pull-up resistor is. We have it for all, right? So wherever this going to the logics inside, wherever the case might be, right? The gates. Now we have one. We can determine the clock frequency, right? This is the clock frequency here, the switching frequency that we will get for the PWM, right? PWM, right? And PWM, right? We just pull this aside here. Pulse width modulation, right? So we pretty much have one inverted, right? So we have PWM 1 and 2, and we have the clock. So if this is 1 megahertz, this guy will be the same 1 megahertz, right? Same clock, right? Unless we divide them down, we could do that, right? But let me say regularly, normally we have 1 megahertz, 1 megahertz forever, right? We have a dead time control, right? Let's put that so one channel here, and maybe let's put like right. So we have the time control happening in this 2 region here, right? 2 region, and so yeah, so this 2 region here, the time control, and I don't know why I choose something that not too nice. Okay, look at the size of that. I don't really have a pen or a pencil or something, but I guess whatever, right? So we had the time control, right? DT, right? DT, the time control, right? DTC, whatever. So we want to say, okay, this side here, if we leave this floating, it could be 5 volts, it could be 5 volts, it could be like 1, 1, 1, 1. But let us say we kind of like bridge this one out here, we bridge this one out here, so it will be 1, 0, 1, 0. So we could do many combination here and thing, right? Same thing for here too as well. We could bridge this one out, we could bridge this one out, we could bridge this one out, and we end up with 0 0 1 0. So we can have different combination itself. So we can determine the dead time control by doing this, and we can determine the clock. So we could pretty much, if we put like probably 100 megahertz, and we do this, and it could divide down to any combination of switching frequency we want, and we could have different nanoseconds or microseconds dead time control. Because the thing about this now, this when I design a motor driver, a class A amplifier, pulse width modulation, right, device for RF amplifiers, pulse width PW, SMPS, switch mode power supply unit. So whatever I design in that require, which is plenty pairs of MOSFET, require certain um, different type of ICs, like how we have ICs specialized for different things. I don't want to design something that have this one particular design application. I want to use this IC for almost any application. They pretty much they have programmer IC, but to achieve this is kind of pretty. You can achieve this in programmable. This you could do it too as well, but it's real tedious itself, because the logic to go about writing this code to do it is tedious, right? Even much less to actually make it in digital IC. So anyway, now I determine in this, so you can see like 60 megahertz, 1 megahertz, 500 kilohertz, 550 kilohertz, 120 kilohertz, 2 megahertz, 4 megahertz, 8 megahertz. So different combination here, we could get these different frequencies itself, right? So that is fine. Now if you want to actually get certain frequency that not over here, and you have a clock, you could pretty much have a next oscillator outside itself with a predefined frequency, and you map it out to get whatever you want to get. You could do that, right? But this is the fixed frequencies that will be divided, right? Same thing with the dead time control. We had the dead time control, which has 16.2 nanoseconds at 60 megahertz, right? We can have these guys here, we can have these guys here. So your application range. So this here I actually did, right? And I already run this signal already, right? So I already map all the signal here, and let us go to, this is sim, right? So because we run a simulation, we will have this in this one here. So there's a no, we want to know exactly. Now forget about this one over here, because this is the entire processes, right? Clocks on them for the digital. So once you confirm your logics itself over here, this is your clock here, right? These are your clock. Well, you have one clock signal, which is the master clock here, and we have, let me go back here. I'm going to scroll in. We have the A and A with the audio coming in. So whatever logic you're designing itself, you will have like the logic happening. But the thing about it, you just take a NOT gate, which is an inverter, and you just get the exact 180 degrees, right? So you have a on time, a very low on time, a high off time, right? So this is what you're seeing over here, PWM, right? So we have a sine wave itself, right? A sine wave itself actually that happening, right? So this is basically what it's going to look like. Let me just right. So what we're going to do over here, we have a sine wave, right? And we have a triangle wave, right? triangle wave, and the sine wave itself literally going so that basically mean we have off time here, then we have a on time which is really narrow, and we have a off time. This thing really kind of mess, so we got this kind of like run a long sine wave here, and we will kind of like do that here, right? So when you look at it, this over here we have like, let us change this color to put something like orange or something, right? So this one here will be on time, this one here will be off time, on time, and notice it's better transition to, right? On time, off time. So you get a drift here how this works, right? Right, so let's bring back amplitude, but you notice the duty cycle change. This is basically what this comparator doing in math on that, right? You could do that by code too as well. So this way, watching over here, we have a peak over here, and we had a duty cycle. So let us look at here, right? You can see the difference over here, right? So we have a more on time here, and then we have a less on time here, right? A less off time here, more off time here. So this is the pair now, the PWM now will be going for the MOSFET, right? Now if you send this to the MOSFET, the pair of MOSFET is going to blow, it's going to damage, right? And this one damage, right? So what we would do, right, we could do this, right? I will just kind of like show you what this look like. Right, so let me look at this for instance, right? Well, okay, I have a pencil here. I don't know why it is I wasn't seeing that before. So we have a MOSFET, right? Let us look at a MOSFET here, and this MOSFET, right, coming along here, and we have an next MOSFET here, right? Be it ground or negative or positive, but we would just take it to be ground, right? And we have this MOSFET here, right? So now we have an output over here, which is fine. Now we just say we have a 10 volts over here, whatever the case. Now if we send this, right, this square wave here, right, which could be if we send this square wave to here, and we take this one here now, and let us call this this could be M1, M2. So we send M1 here, right? M1, my bad. We send M1 here, we send M2 here, right? So basically we put M1 and M2 there. Now I'm going to zoom into this region over here, right? This region. So the rise time, now when we zoom in, we have a rise time here, on time, and we have a fall time. Now the other one that actually they over here are going to join the two of them, right? Are going to put a center transition here, right? Voltage. Let me say this is 0 volts, and this is 12 volts for the gate, right? Let's say this is 6 volts. Okay. Now I should use a different color here, right? And we have a on time here, and the transition here now is like this. Now let's kind of draw this out here, right? So this is basically what's happening here. We just draw this on back here. I just should kind of like use, right? This is for everybody to see. Right, so we have the situation where we have um, this is M1 and this is M2, right? Now we zoom in straight to the transition over here. At 6 volts, this gate already conducting already. And just to show you that, let me get a data sheet of a, a FET. Right, so we have a MOSFET here, so everybody class the amplifier MOSFET. Now if you look at the gate to source voltage, right? Gate to source voltage, right? Where it is, gate to source, right? I charge, right? I pass that. Okay, so here what we will do, they have 10 volts over here, right? Let me go down to the this way, drain to source, right? Drain to source voltage, drain to source voltage, gate to source. This is the one we want to get here, right? Right, so we have drain to source current, right? So we have a current over here which is showing us here more voltage go is more current come up, right? So look at 5 volts here and 4 volts, right? 5 volts we don't have any conduction resistance, so it's a conducting current. The more the voltage go up to 10 volts, we get more current because the ohmage is going down to the drain to source, right? So the current will go up obviously. So this curvature here, right? This is a trace graph. This itself. So you could pretty much have software to measure this to get its accuracy. When you're doing engineering, you need to get this information out, right? I forget the name, how to call it, but I create one and I have free one outside if open source, so I'll show you what it is. So yes, so at 5 volts now you can measure this and calculate the current and the impedance itself. So even though the data sheet here, the data sheet have some information, right? Voltage plus minus 20 volts will go up to, they're showing you the voltage they use to actually conduct at this current here. 10 volts we get 49 amps, this is 49 amps, 35 amps. Temperature itself, right? We kind of like go here and we say okay, 25 degrees, right? The thermal junction, right? 40 something amps. This is logarithmic, right? And here's linear this side, and this side up is logarithmic, right? So you just have to be careful when you're doing that, right? So you kind of like look for wherever it is, you get a 40 something and you get the 10 volts itself, right? So you got to run through all those things. So anyway, so what's going to happen in this point over here is, let us say we have around this region over here we have 4 volts, right? And 4 volts over here. So from this region over here now, my bad, they say this region, oh gosh, I'm kind of making this bad, right? This region over here now, we're going to have a wave pattern looking like, let me draw this over here, right? And let me just do over here, right? So I want to draw a wave pattern over here, right? So you have a heavy current over here. So for this MOSFET here and this MOSFET here that drawing current, right? We can have one cycle current going this direction, and then we have next cycle current going this direction, right? So when you switching this one on, right? So M2, M1, we have a current going this direction. So this current, let me say this current is, let me just draw a chart here. This is 0, we have a current going at here, right? And this side here we have a current, at this point here we have a current going here, right? Over here we have a current going here. We call this 10 amps, right? 10 amps, right? So we have 10 amps here, 10 amps here for both of them, right? And now I didn't bother to put current over here, right? In fact, I should do that, right? Let's say we have a current over here, and next one now we have a current here, right? and then we have a current over here. What is happening is that we will have a waveform looking like this, going up to like this, and transitioning like this, right? So we have a current coming down like this, right, and a current going up like this and transitioning here, right? So this is the situation where you get overshoot, right? So overshoot will register as a ripple here, right, and a ripple here. But if we actually draw this in a line, right, it could be like a heavy current, right, and a heavy current like that, right? So we gonna get like this. So you're gonna get overshoots and undershoots, but you will see certain ripples happening over here, and these ripples is start to radiate out, and this undershoot here is radiating out, oscillating, and this is a spike. So when you see over here, I will draw how it look like, right? Right, so you measure over here and over here, you find time, and time now you have a RC circuit resistor capacitor equal F, and 1 over F is time. So you basically work this out and you get RC circuit, and what you do now, you put a capacitor and a resistor here to ground, right? So this here itself, if we have, let us say we have this MOSFET can handle 30 volts, right? And we say we have like a 30 volts, forget the gate here now. Let's say we have a square wave. We have let's say 25 volts we have here, right? 25 volts. But this spike now add an extra 10 volts. So when you add extra 10 volts, you end up with 35 volts. So now we have 35 volts for 30 volts device, 5 volts extra, right? So this 5 volts extra now going to blow this transistor completely out of the planet. So before we do that, what we need to do, we need to actually find this frequency and snub it down. Now Texas Instruments create a software that doing it. A couple of years ago they do it, but way years ago, probably about 15 years at least, I already developed a software doing it with precision detail, not like with Texas Instruments 1 or 2 inputs and that's it. I have like the full entire works. I have a guy who write a whole book on snubber itself. All electronics just have this ringing thing, stray inductance, capacitance, and stuff like that, and ringing itself and whatnot. Gate is have capacitance like this, right? These things is how to calculate these things, and you will find it in the data sheet as right. So here we will find it in the data sheet, right? It will be these guys here, right? So you will see it here, the Q, right? This is total gate capacitance, this here. So this is nano column, right? Higher nano column, meaning now let us kind of like look at this here, right? So what basically mean is, right, so this region here itself, so this is like let's say this is a gate of a MOSFET. It is pretty much like a capacitor, right? It's pretty much like a capacitor, but let me say this is a gate, right? This is a gate itself here, and this is the source, right? So when you have a voltage going across, this is a capacitor you need to charge. So when you have to charge now, you with a square wave, right? It coming on, so remain on is not a problem. The problem now is this capacitor is take a time to charge, right? This is where the current occurs in charging a gate, right? So how fast you can charge this is where you're taking the current. So the faster the frequency is more current it pull, right? So that is a serious thing, more current, right? At rise time. And the discharge this is fully charged, you have to discharge this now, so the off time, right, could be like off, take a while to discharge. So this is where the current come in, and this is where it lose energy in the rise time and fall time, right? So these things, everybody have a gate in it, right? And so anyway, this is how this works, right? Now we look at this is for simulation to confirm your logics itself, right? You just kind of yeah, plenty zoom in. Computer pull resources because of that, right? So I'm running out of RAID right now. You're reading out of that. That's for this. Recommended when you're doing things like this that I have RAID SSD, right? Um, yeah. So there's a pin in it ass there, right? So we go to this one. Hope right now. I had to do to synthesize my Verilog, or if it VHDL system Verilog, whatever it is using, or Tickle, whatever. I created so this is my project file itself here, and as you can see here, open as text, right? So this is create a synthesize to synthesize my logics. So as much as this looking simple, you have to use your brain itself to be able to do this, and you create a test bench yourself, right? So my bad, there you go again, right? So this is my Verilog here, and this is my constraint, right? So whatever, and keep on doing that, right? So after everything done compile itself, you look at the schematic, right? So let's look at the schematic now. You would like to see what your logics look like in schematic, right? So as you can see over here, we have the inputs itself, we have the divider itself, and we have all the logics here. Cool. So everything looking big here because it is, right? So this is everything here. So anyway, now you have to do, if you have to go to virtualization Linux, you will have to do this place and route, right? And then we're gonna do schematic versus the VHDL code, the layout versus VHDL code. So layout versus schematic, LVS, right? So pretty much the schematic is a representation of the VHDL code, the hardware description language. So you could actually make sure that your layout is in reference match 100% with your schematic or your VHDL, to make sure that before you fabricate itself, there's a bunch of different tools itself involved. So yeah, this is what it look like. So what I'm going to do in Cadence now, before I go into Linux to do anything, what I'm going to Cadence to do, I'm going to actually manually build all the logics itself over here from the schematic, and once I do that, I will pretty much think. Now we have right, we could do a Verilog file here itself, so I will do a Verilog itself and do a test bench and run every single thing here, and then I will do the schematic, the logics itself. So I will do Verilog itself, and once I do those things, I will do some confirmation here before I go on to Linux and do the IC. So what I'm going to do here now, all my designer will have this programmable. We could do through software or hardware externally, but I may not put hardware. I'll do everything firmware, right? So I have to build some memory.